Right now, that massive shade tree in your front yard, it might be literally rotting from the inside out.
Yeah, hollow as a drum.
Right. Just completely hollow, but looking perfectly green and healthy on the outside. Or maybe it's like actively fighting off this silent insect invasion by pumping out sticky sap.
Which is an incredibly energy-intensive process for the tree.
Oh, totally.
Yeah.
But we look out at our yards and we just see these, giant pillars of wood and leaves. We assume permanence. We just see scenery.
Right, we think of tree care as just another weekend chore.
Yeah, basically like mowing the lawn,
Hmm.
but taller.
And that is a really dangerous oversimplification. I mean, you are walking underneath a landscape of intense, highly volatile biological drama.
It's crazy to think about.
It really is. It's a constantly shifting battleground of, fluid dynamics, structural physics, and literal chemical warfare happening right above our heads.
Well, welcome to this deep dive. Today, we are completely transforming how you look at the canopy over your roof. Our mission today is to pull you out of that yard chore mindset and plunge you into the really complex, hidden science of urban arboriculture.
It's a fascinating world once you really look at it.
It is, and we're drawing our insights today from a really comprehensive collection of field strategies and biological data from West Covina Tree Service.
Right, and they manage tree canopies in Southern California.
Which means they are dealing with some of the most, extreme climate pressures imaginable out there.
Exactly. Droughts, winds, you name it.
Yeah. So whether you are trying to save a beloved oak tree in your backyard, or you're just wondering why the city crews are suddenly dismantling the trees on your street, we are going to give you a massive aha perspective on the living infrastructure all around you.
Framing it as living infrastructure, I think, is crucial here. Because when you understand the plant biology, like the literal cellular mechanics of how these organisms function and heal and communicate, you realize that human intervention is really the razor-thin line between a landscape that thrives and, well, a multi-ton liability waiting to collapse.
Okay, let's unpack this by starting with the most common thing humans do to trees, right? Pruning.
Right. The classic trim.
I think the universal misconception is that pruning is basically just a giant haircut.
Oh, completely.
Like the tree gets a little shaggy, branches are hanging over the driveway, so we get up there with a saw and just, hack it back until it looks neat.
And viewing it as a haircut just completely ignores the biological reality of what a cut is.
Because hair is dead.
Exactly. Hair is dead tissue. When you saw off a branch, you are intentionally amputating a limb from a living organism.
Wow, amputating.
Yeah, it's a surgical procedure. It requires a real understanding of cellular biology because if you leave an open wound, you're just inviting in decay that will systematically hollow out the organism.
See, we shouldn't be thinking of pruning as a haircut at all. We need to think of it as a surgical procedure. And I was amazed to learn just how precise this surgery has to be.
It is incredibly precise.
Like you can't just saw off a branch flush against the trunk to make it look smooth.
Yeah.
There's this very specific anatomical target called the branch collar.
Right, and the branch collar is the entire key to a tree's immune response.
So what is it exactly?
Well, it's that slightly swollen, kind of wrinkled wing of bark right where the branch merges with the trunk.
Oh, I know you're talking about the little bump.
Yeah, exactly, the bump. Arborists target that specific area because it contains these specialized, rapidly dividing cells.
Okay.
So when a cut is made precisely at the outer edge of that collar, those cells mobilize. They multiply and physically roll over the cut wood almost like melting wax.
Like melting wax? That's why?
Yeah, it creates this hardened callus, and this process mathematically seals off the exposed internal tissue, which stops, fungal spores and bacteria from entering.
But, what if you cut too close? Like if you shave off that swollen collar?
Well, then you've just destroyed the healing factory.
Oh, no.
Yeah, the tree cannot form a callus, the wound just stays open permanently, and rot goes straight into the main trunk.
That's terrible.
It is. And on the flip side, if you cut too far out and leave, say, a 6-inch stub.
Right, just a random stick poking out.
Exactly. The healing cells at the collar can't stretch that far to cover it. So the stub dies, it rots, and it basically acts like a hollow straw, funneling disease right back into the core.
It really is precision engineering.
Mm-hmm.
And then there is the sheer volume of what you're cutting, which is governed by something called the 25% rule.
A very, very important rule.
The data shows that if you remove more than a quarter of a tree's foliage in a single season, you induce severe, sometimes even fatal biological stress.
Because you're starving it.
Right. And wait, if a tree literally starves when it loses its leaves because, that's how it photosynthesizes, why are we cutting any live branches off at all?
It's a fair point.
Doesn't any cut fundamentally hurt the tree?
Well, this raises an important question.
Yeah.
And the answer is that it's a calculated biological trade-off.
A trade-off, how so?
Yes, an open wound is a short-term stress. But you are exchanging a minor localized stress for long-term structural integrity.
Ah, okay.
You are intentionally directing the tree's energy.
Hmm.
Left to its own devices in an urban environment, a tree might, grow a massive, heavy limb right over your house.
Which is bad.
Very bad. By making a strategic cut at the branch collar, you basically tell the tree, stop sending resources here, redirect them to the central trunk.
So we're kind of like programming its growth pattern.
We are, and that is why a professional doesn't just, trim a tree. They execute specific techniques for specific biological goals.
Like what?
Well, consider crown thinning. Every 3 to 5 years, an arborist will do this because an incredibly dense canopy acts like a sail in a windstorm.
Oh, so it catches all the wind and could rip the tree down.
Exactly. And it traps stagnant, humid air, which is a perfect breeding ground for fungal infections. So an arborist will selectively remove interior branches, always obeying that 25% rule, of course, to allow wind and sunlight to physically penetrate the canopy.
Okay, so how does that differ from something like crown reduction? Because, they both just sound like making the tree smaller.
Right, but crown reduction is a highly specialized height control measure. It's usually done every 2 to 4 years to keep trees out of, say, high voltage power lines.
Right.
Instead of just chopping the top off, which causes the tree to panic and shoot out these really weak, unstable branches, an arborist carefully cuts specific vertical leaders back to lateral branches.
Well, they find branches that are large enough to take over.
Exactly. They take over the dominant growing role. It lowers the height while maintaining the natural structural geometry.
That makes a lot of sense. And for the young trees, there is structural pruning. Learning about this really changed my perspective.
It's crucial for long-term health.
Yeah, you do this every 1 to 3 years, not to make the sapling look pretty, but to train a single dominant vertical trunk.
Right.
Because if you let a tree grow 2 main trunks that split off in a V shape, as they get massive, they will eventually just peel apart under their own weight.
Yeah, that V shape basically creates a wedge. And as the tree grows, bark gets trapped between the 2 trunks, preventing them from fusing together.
Oh, wow.
So decades later, a strong wind hits, the wedge splits, and half the tree just tears off. Structural pruning prevents a catastrophic failure 30 years before it even happens.
That's amazing. And timing this surgery is also critical, right?
Timing is everything.
For deciduous trees, the ones that drop their leaves late winter, is the absolute best time to prune.
Yes, because they are completely dormant.
Right. Because the sap isn't actively flowing, a cut doesn't cause them to bleed out, so to speak. They heal the wound quietly and push all their stored energy into explosive spring growth.
Exactly. You perform the operation while the vascular system is at its absolute lowest pressure.
So what does this all mean if a pruning cut goes wrong? Or if nature simply inflicts a wound? Like, how does a tree communicate that it's sick?
That's a thing. They do communicate.
Yeah, because they don't just suddenly fall over without warning, right? Reading through the arboricultural notes, it's clear they are constantly displaying their body language.
Oh, totally. A tree's visual distress signals are profound if you understand the anatomy.
Let's run through these signals. The field guides flag crossing branches as a major early warning.
Yes, very common.
2 branches rubbing together in the wind might sound harmless, but that friction physically grinds away the bark. It's like walking around in wet shoes. Eventually you get a blister, the skin breaks, and suddenly you're wide open to a terrible infection.
That is a perfect analogy. The bark is literally the organism's skin. It is the primary hardened armor.
Right.
But right beneath that armor, like fractions of an inch deep, is the vascular system. It's the plumbing inside the walls of a house.
The phloem and xylem, right?
Exactly. Actively pulling water up from the soil and pushing sugars down to the roots. When branches rub and scrape away that bark, you have just busted open the plumbing.
Oh, wow.
Yeah. Pathogens, airborne bacteria, insects, they now have direct, unfiltered access to the tree's bloodstream.
That perfectly explains the next distress signal. If that infection gets into the plumbing, the tree might experience unexplained leaf drop or heavy discoloration right in the middle of the summer growing season.
Right, like in July.
Yeah.
Summer is when a tree's internal water pressure should be at its absolute peak to sustain all those green leaves.
Right.
If it is dropping leaves in July, the plumbing has failed.
It's literally failing to pump.
Exactly.
Yeah.
The vascular tissue is so compromised by decay or root damage that it physically cannot pump water high enough to support the canopy. The tree is abandoning its outer extremities just to survive.
And you see this visually. When a tree accumulates dead wood localized purely in the upper crown, it's hoarding energy downward, retreating closer to its vital organs.
It's a very clear sign of distress. And arborists will actually do a deadwooding procedure annually just to clear those fall hazards.
Right. But the most alarming distress signal, the one that really caught my attention, is the fungal bracket.
Oh, yeah. The bracket.
You know those little shelf-like mushrooms you sometimes see growing directly out of the side of a main trunk? They look kind of whimsical, like something out of a fairy tale.
What's fascinating here is that those whimsical mushrooms are actually the fruiting bodies of wood-decaying fungi.
Oh, yeah.
Yeah. And their presence on the outside of a trunk tells a horrifying story about what's going on inside.
How bad is it?
Well, to understand this, you need to know that the center of a mature tree, the heartwood, is a dead, rigid spine made of complex polymers like lignin.
Okay.
It provides the immense structural strength that allows a tree to stand upright. The living part of the tree is actually just a thin cylinder wrapped around that dead spine.
Wait. So the core of the tree is already dead. Why does it matter if a fungus is in there?
Well, think of a skyscraper. The steel beams are dead metal, right? But if a chemical starts dissolving those beams, the living people in the offices are going to have a very, very bad day.
Oh, right. The whole thing comes down.
Exactly. When you see a fungal bracket on the bark, it means the mycelium, the root-like network of the fungus, has already penetrated deep into that rigid heartwood spine and is actively dissolving the lignin.
The structural core is turning into mush.
Yes. The tree is decomposing from the inside out, even while the outer layer of leaves might still look perfectly green.
That is terrifying.
It really is.
And these massive organisms don't exist in a vacuum. After looking at surgical cuts and internal rot, we have to zoom out to the environment.
Right, the macro level.
The West Covina data is fascinating because Southern California is an ultimate climate stress test. You have extended dry spells, severe prolonged droughts, and those infamous Santa Ana winds.
It forces urban arborists to view the tree not as an isolated object, but as a reactive participant in a very extreme microclimate.
Here's where it gets really interesting for me. My assumptions were completely challenged here. I always viewed mature trees as invincible pillars.
Most people do.
Like their roots must go incredibly deep, right? I assumed a drought just made them thirsty. But the research shows that a lack of water actually turns off their immune system, leaving them completely defenseless against bugs.
It's a fatal chain reaction.
I get that drought makes a tree thirsty, but how does a lack of water physically cause it to die from a bug bite?
If we connect this to the bigger picture, it comes back to that internal plumbing and fluid dynamics. We tend to think a tree's only defense is its hard bark.
Right.
But a healthy tree possesses a highly pressurized, active defense mechanism using sap.
Sap as a weapon.
Yes. Take the bark beetle, which is one of the most devastating pests in California. When a bark beetle tries to chew through the bark to lay eggs in the vascular tissue, a healthy, fully hydrated tree detects the breach.
Okay, and what does it do?
It immediately mobilizes sap to that exact spot, pumping it out under high pressure. It literally flushes the beetle out of the hole and entombs it in sticky resin.
Wow. It's literally chemical warfare.
Precisely. But producing that sap requires massive amounts of water.
Ah, I see where this is going.
Yeah. During a severe drought, the tree's water pressure just plummets. It physically cannot manufacture sap. And bark beetles, they communicate through pheromones. They can actually sense when a tree's defenses are down.
So they know the tree is weak.
They do. They swarm the stressed tree by the thousands. Without the sap to push them out, they bore freely into the vascular tissue, lay their eggs, and the larvae chew a ring entirely around the trunk.
Completely severing the plumbing.
Exactly. A tree that survived for a century can be choked to death in months just because it lacked the water to create sap.
That's brutal. And surprisingly, those critical roots aren't tapping deep underground aquifers.
No, not at all.
Most of a tree's structural and moisture-absorbing roots live in the top 18 inches of soil.
Which shocks a lot of people.
Yeah. They stretch out incredibly wide but incredibly shallow, which means when the topsoil bakes in the sun, the tree dehydrates rapidly.
And this is why the canopy and the roots are one continuous biological loop. A properly pruned tree doesn't cast a solid block of dark shadow. It casts what arborists call dappled shade.
Right, like a mix of light and shadow filtering through the leaves. But I thought that was just an aesthetic term.
It's an active environmental cooling mechanism. By filtering the sunlight, the canopy significantly lowers the ambient ground temperature directly over its own root zone.
So it's protecting itself.
Yes, this drastically reduces the evaporation rate of soil moisture. The tree is literally air conditioning its own roots to maintain its sap pressure.
It's regulating its own microenvironment. That is so cool. And it goes beyond just casting shade. The organic material, the leaves and debris the tree drops onto the yard, plays a vital role too.
Right.
And we usually just rake all that up and throw it in the green bin.
Which completely strips the soil of necessary nutrients.
Well, really?
Yeah. As that organic matter decomposes, it fundamentally alters the soil chemistry. It creates this spongy layer that traps moisture and supports beneficial soil biology.
So by cleaning it up, we're actually hurting the tree.
Exactly. In an urban environment where we clear away that debris, we have to artificially replicate it.
How do we do that?
That requires deep drip line watering, applying water slowly at the outer edge of the canopy where the absorbing roots are, and using proper mulch to basically mimic the natural forest floor and lock that moisture in.
Okay, but despite all the deep watering, the precise surgical pruning, and the microclimate management, sometimes the biology just fails completely, right?
It does. It's an unfortunate reality.
Roots rot. Fungi dissolve the spine. And that brings us to the tipping point.
The point of no return.
Right. The terrifying transition from routine maintenance to high-stakes emergency engineering.
Recognizing the exact moment a biological organism transitions into a physical liability is really the most critical responsibility of any property owner.
Because you can't just fix it anymore.
Exactly. Because when the structural integrity crosses a certain threshold, the organism cannot be saved. It must be dismantled.
The warning signs of imminent collapse are chilling. We aren't talking about drop leaves anymore. If that 10,000-pound oak leaning towards your bedroom roof starts showing signs of soil heaving at the base, it's a catastrophic red flag.
Absolutely.
Visualizing soil heaving gives me a pit in my stomach. It's like seeing the concrete foundation of your house cracking. If the anchor snaps, the whole thing goes.
Oh, right. To really understand soil heaving, you have to look at the physics of leverage.
Okay.
A massive tree is essentially a giant lever. The trunk is the lever arm, and the root system is the counterweight anchoring it in the earth.
That makes sense.
So if a tree is leaning heavily to the left, the roots on the right side are under immense tension, pulling down to keep it upright.
So they're like the ropes on a tent.
Yes. If you see the soil suddenly bulging or cracking open on the right side, it means those tension roots have literally snapped underground.
Oh, man. The anchor has physically broken.
Exactly. The tree is no longer secured. It is merely balancing on its own center of gravity, just waiting for a single gust of wind to pull it over.
And when a winter storm hits West Covina with saturated soil and high winds, those compromised trees fail.
They do. They uproot entirely, or massive limbs fracture, crashing onto houses.
This is where emergency removal comes in. And they don't just, walk up with a chainsaw, cut a wedge, and yell timber to drop it in the yard.
No, definitely not.
The field notes detail the extensive use of cranes. Why can't you just fell a tree the old-fashioned way if it's already dying?
Well, because the geometric math and the sheer kinetic energy won't allow it.
Really?
Yeah. A mature, waterlogged trunk can easily weigh 10 or 20,000 pounds.
Wow.
In a dense urban environment, if a failing tree is suspended over a roof, you do not have the physical clearance to let it fall laterally. The impact force would just pulverize the house.
So you have to eliminate the kinetic energy entirely.
Exactly, by lifting it straight up.
That is wild.
Professional arborists rig the tree to a massive crane. The crane operator takes the exact tension of the branch's weight. Only then does the climber make the surgical cut.
So that doesn't even fall.
Not an inch. The severed multi-ton piece just hovers in midair, and the crane slowly swings it away and lowers it safely to the street. You are basically dismantling a skyscraper from the top down.
It's heavy industrial engineering wrapped in high-stakes logistics. Because if a tree does hit a house, fast extraction involves emergency tarping to stop immediate water intrusion into your living room and specialized documentation for your homeowner's insurance.
Right, because they need photographic proof of the failed root system or the internal rot just to process the claim.
Which is exactly why proactive removal is the goal, right? Waiting for a storm to expose a failing root system is just gambling with your property.
It is. And arborists strategically plan complex removals for the winter.
Why the winter?
Well, the trees are dormant, meaning there are no leaves, adding hundreds of pounds of extra weight or acting like wind sails.
Smart.
Yeah. And the ground is cold and firm, which provides a solid platform for the heavy crane outriggers. It is a controlled, calculated demolition rather than a frantic emergency rescue.
So we've gone on an incredible journey today. We started with the microscopic biological precision of a single surgical cut at the branch collar, exploring the 25% rule and how trees physically manufacture a callus to seal their wounds.
It's amazing biology.
Truly. We learned to translate the silent body language of distress, from the blistered plumbing of rubbing branches to the horrifying reality of fungal brackets dissolving the tree's internal spine.
Right.
We zoomed out to the environmental battleground, discovering how drought disables a tree's sap defenses against bark beetles and how dappled shade actively air conditions the root zone.
A fully connected ecosystem.
Exactly. And finally, we explored the intense physics of root failure and the top-down geometric dismantling of a 10,000-pound organism suspended from a crane. The next time you look out your window or walk down your street, I guarantee you will no longer just see scenery.
No, absolutely not.
You will see a complex, highly active, fiercely struggling living infrastructure.
And we are intimately connected to that struggle, which leaves us with one final thought to consider.
What's that?
Well, if a mature tree acts as a keystone, actively filtering sunlight, cooling the ground temperature, maintaining the soil chemistry, and supporting an entire microscopic ecosystem beneath its canopy, what happens to the invisible biological network of an entire neighborhood when just one massive historic tree is abruptly removed from the grid?